Hello everyone, welcome to the Radiation Control and Safety Lecture, quarterly lecture for those that are operators for the AGN 201 at ISU. Shall we begin? I'll try and give you some good information. If you have any questions, go ahead and let me know about them. I'll do my best to answer them later. So, I'm going to start off with talking about the survey meters, things that we can pretty much like the pancake probes that we used to be able to read gamma and beta. So the main thing that this would be used for in your guys' situation would be to examine gloves, your feet if you're in a spill situation. So the first thing that you should be doing is checking the instruments to make sure that they are within the calibration period. ISU is now doing an annual period, so our periods between calibration are a full year instead of half a year. So make sure it's within calibration. There should be a sticker on the side that should have a calibration date and who calibrated it, whether it was Qualitech or if it was by somebody in the EHS office. Depending on the instrument, sometimes we have to send them out. So check for calibration date. Then we should check for we should make sure that it has been source checked. Meters should be source checked daily to make sure that they are maintaining their calibration. Things can happen, they can go out of calibration earlier. One of the reasons for that could be that some kind of damage occurred that wasn't known about, like it got knocked over wrong, or it fell, or it got hit by something accidentally. Damages can occur, and that can throw it out of calibration, or just little things. So it's one of those, it's always good to make sure that it's within its operating limit. And that's how we use the source checks. I do them at the EHS office once a day, especially when I know the meter is going to be in use. We also maintain 2 safety meters there. Okay, so you make sure it's in good condition. You check for the calibration. It should be source checked. You also check for the battery level. If it's not maintaining a good battery level, then you can't trust what it's reading. You should be, it should fall within a little check area. When you click it to battery, it'll tell you if it has good enough battery range to be able to perform its function. Next thing you should do after that is select the proper scale for the survey. So if it's a low level area, you can select the lowest range. It's a higher level area with a higher background. That's where selecting a certain range should make the biggest difference. If it's really low levels, you can turn on the lowest level and then you can pick up really well. But if it's going to have a really high background, maybe that instrument wouldn't be a good choice for actually detecting how much, what kind of contamination you're dealing with. So that's our final bullet point on this, is to establish the instrument's background reading. And it's always good to know where that sits and keep it in mind, because when you're surveying the area that you're checking for contamination, if it's about twice what background is, then that area or item is contaminated, and then you should follow the proper procedures to continue wise. So you've completed all this. You checked the instrument for calibration. You've made sure it's source checked. Battery level is good. You put it in the proper range, and you know the background. This leads you to step 2 of survey techniques, and this would be to proceed to survey, which you're surveying, like something you'll do in the Reactor lab a lot is when you've used gloves for handling something, then you go and frisk survey them afterwards to make sure that they are low levels of any level of contamination. We don't want any contamination. If there is, it's rad trash. If it comes back clean, then we can dispose of them through normal garbage, which is the better form, because the less radioactive trash we generate, the better, because it's easier to deal with. We don't have to go through as many steps to be able to dispose of it. So the less radioactive waste we make, the better. So for frisk surveys, you survey the area with a speed roughly 1 to 2 inches per second, about half an inch from the survey location. I kind of, for example, with the pancake probe, I try and make S patterns myself over the region so I can get a large picture when it is. If you start having large spikes in certain areas, you should come back and hover over those spaces to where you can get a good idea to see if it was just a bits of spikes just because cable noise. I've had situations where the cable got tweaked and it caused the needle to jump. It's always good when you see that to come back and inspect it multiple times. Another good option for being able to tell is when doing frisk surveys or any kind of survey is to turn the audio on. It makes it to where you don't have to be watching the dial face to be able to know what it's reading. You can get an idea of if there's some kind of contamination by what kind of ping sounds you hear. If it's a large amount of pings, you know it's it's at least slightly contaminated. If you are barely hearing just the slight ping ping, that's kind of normal with the background. You know you don't really have much. So that's good procedure. It's good to have the audio on. Yes, it makes your ears ring, but it helps with you being able to keep track of radiation levels. This is the reason it's a good idea when you put the detector on top of the reactor console to leave the sound on, even if it's at a low level, because that way when you're operating, if it starts making a lot of noise, you know that you're getting higher levels, and if it's not something you should be predicting with what you're performing at that time, you know there's a problem. Okay, so now we're to the point of, okay, what if there is contamination on the area or the tool that you just surveyed? You should proceed to notify people and the others in the area so they know about it, because you don't want them walking into it accidentally. Then you should proceed with proper procedures for decontamination and contacting those that should know about this with when it comes to our procedures. What do you go through? Who should be contacted? What orders? It depends on the situation, of course. So that's something to keep in mind. Like for example, you may want to be getting hold of EHS, come and decontaminate it. We have a kit set up for situations like that. If there's massive contamination. Some of you may have already set up and kind of went through something like this for the safety drill that happened a month ago. So that helps us know what to do and what safeties to establish and the proper methods of dealing with radioactive contamination. So good things to keep in mind. Our instruments, our frisks, are there to help us be able to know what we're dealing with and how to keep ourselves safe in the situation of dealing with those kind of contamination. It's also good when you're in like in the source vault, for the same reason that we carry a meter back behind the protective bricks next to the reactor, so you know what kind of levels you're getting. Once again, for safety, it's good to know if you're getting in really high levels, you don't want to be staying there as long. Once again, following the LARA principles, as low as reasonably achievable. So if it's a higher level, you don't want to be around it as long. STDs, right? Max always talked about STDs. Yeah. So time, distance, those are two major things for the STDs. And shielding's another big one, but if you're having to be exposed to an area, it's one of those, how long you spend back there is going to make a big difference on how much how much of a dose you're going to get, and that's something that will be read upon your dosimeter when they're collected quarterly. Also, the further away you are, the better it's going to be. So it's one of those, when you're in a small space such as the isotope vault, the less time you spend in there, the better for you. Or like our rabies source that we use for a startup source, we want to keep nice distance. That's part of the safety as well. Times, distance, shielding. Okay, so dealing with contamination. There are two different types of contamination. There's removable contamination and fixed contamination. So, when it comes to removable contamination, as is implied in the name, it's able to be removed. We want to be able to get rid of it. So, removable contamination we can find out through taking swipes of the lab areas, like some of you have seen me do from my job. I'm in there for like the SCA. I go through with swipes, and I swipe to see if there is removable contamination. Another example of that would be some of you saw with the 10% survey of the plates in the SCA. That would be considered a leak test to see if the integrity of the fuel is giving out, and if it's leaking removable contamination, then we have to be disposing of that. There's a certain level that is within safe for leak tests. We leak test all the sources in the source vault, for example, be able to see if their integrity is holding up as well. And the way that we test all these different swipes is for EHS at the moment we use an LSC. We're soon going to be getting some proportional counters for the higher level places such as like the Reactor or the Idaho Accelerator Center. So that's how we can assess to see if there is removable contamination. If there is removable contamination, what do? We go in and we try and remove it so it's no longer a hazard for anybody. The different hazards that come with removable contamination is it can be internalized. You could end up within your lungs, digest accidentally, etc. It's also giving you external exposure, which has same dangers of radiation and all as they normally would. Another problem with removable contamination is then you can spread it. A good way to think about this one, I know some of you have heard of dog poop. I prefer to use the idea of car oil, because the way of thinking of used car oil, it's always nice and black when you dump it out of the car, or you're working on something, the grease and oil get on your hands, right? Well then, every single thing you're going to touch for the rest of the time you're working on it until it's off your hands is going to be turned black. And that could be the nice shirt you're wearing, it could be the steering wheel, it could be the hood. So, a good way to think of removable contaminants to prevent spreading of the contamination is to treat it like your hands are coated in filthy oil and now you're scared to touch anything. It's good to, when it comes to, if you end up with removable contamination on your hands or something, follow the steps for surveying that we had in, let me see if I can, yeah, right here. So when it comes for frisk surveys, that's a good way to make sure you don't have any of the, for example, car oil on your hands. So you're checking by running your hands over the pancake probe of a frisk for a gamma beta detector. So you're taking your hands over it at 1 to 2 inches per second, back and forth, first palm down, going across, and then flip over. Take the back of your hand across about that speed, keeping about a half-inch distance away from the pancake probe. Well, of course, a little leeway on both sides. And by doing that, you can check your hands for that kind of contamination. If you do have contamination, that's when you dispose of the gloves properly and you assess where the contamination came from. So you can figure out where it's coming from so you aren't spreading the contamination. That way you can maintain safety around it. It's not going to end up where we don't want it. And, well, if we know where it is at that point, then we can go in and clean up where the contamination is and prevent it from being more of a hazard. The other kind of contamination, of course, is fixed contamination. So, the way we deal with fixed contamination, it's non-removable, right? So, the way we can measure it and see how much of it's there is by dose rate measurements. We take ion chambers, we go make sure we see how much there is, Geiger-Müller tubes, and we assess how much external exposure you're going to get from that contamination. It is always going to be in that area. There's no ability to decrease it. But at the same time, you stay at equal risk with it at all times. It's always good to assess where those areas are and make sure they are labeled and denoted as having radioactive contamination, to where we know to treat that area in a way that radiation should be treated. We should not fear radiation, but at the same time, we should treat it with respect and not be foolish around it. Try and be safe, keep ourselves safe, keep everybody around us safe, and keep them out of the contamination every chance we can. So yeah, going back to what is contamination, think of it as car oil, think of it as dog poop, whatever way works best for you. It's radioactive material in an unwanted location. We don't want it there. We're trying to prevent it from being there. So it's one of those, keep track of it. We want to keep track of the contamination. We don't want it moving around, because then it becomes harder to clean up. So yeah, it's better if you know something's contaminated, stay away from it. Talk with people who pretty much go through the procedures to be able to clean up the contamination in a safe, orderly fashion to where it doesn't get spread and it isn't harmful to anybody. Okay, so PPE, personal protective equipment. So this comes down to, you want to wear gloves, right? That's something that's talked about. If you're handling the sources, if you're handling the fuel rods, if you're handling things that could be giving off removable contamination, you want to be wearing gloves. You don't handle this stuff barehanded. Of course, gloves aren't going to stop radiation from coming through, but at the same time, for removable contamination, it will protect you. So yes, wear your gloves to prevent contamination. In some places, such as the I Know Accelerator Center, there are labs which you need to be wearing shoe covers in those areas to prevent contamination from being able to be covering your shoes. It's not fun to lose your shoes. I've been lucky and haven't lost mine yet, but I have known people who have. So wearing shoe covers is a nice way to prevent external contamination from being able to be removed from a lab if it's a place where there's lots of contamination occurs anyways. By having it to where people are wearing shoe covers, same idea as the gloves, it gives an extra barrier of safety between you and the contamination. Of course, once again, we don't want to be spreading it. We want to make sure that contamination is cleaned up when found. But for places that have high levels of contamination, no matter what, shoe covers are a great way to prevent you from carrying it outside the lab. So yeah, safety first. That's a big deal with radiation. If it's not going to be done safely, it's not being done right. Ooh, problems with radon. This is a problem for me when I'm doing my surveys, because there are times in which I'll survey a lab that have so low levels there shouldn't be any kind of contamination. They aren't really doing anything in there that should give contamination. And I will run them in our LSC, lightsaber, in the LSC, which, let me get back on my mental track. So yeah, radon's a problem because when I run a sample in our LSC, sometimes it'll come back at action level. And action level is when we have to go and remove contaminants. But at the same time, whenever I have something like that happen, what I do for extra knowledge to know for a fact, yes, that is contaminated, to make sure for the problem of radon, I will rerun a sample. If it comes back above action level, I'll run it 2 more times, and then I take the average. The average tells me, is it really contaminated? If not, it was radon. Radon is a naturally occurring radioactive gas, has a density 8 times heavier than air. So it's one of those, it sits towards the bottom. So it's really prevalent within basement labs. You get up higher into labs that are on 3rd, 4th floor, it's less of a problem. But you go into the basement, such as like the engineering labs are, sometimes we pick up the radon gas. One of the reasons for that is it attaches to charged dust particles. So it's one of those, when I'm doing a swipe, and you've seen them all, it's on a piece of wax paper with a little piece of cotton, swipe on the other side. When I'm swiping an area, I'm picking up all different things that are on contact. A major thing is dust. Meaning, if radon is attached to the charged dust particles, then it goes into the LC, like I was saying, then it comes back saying that the area could be contaminated, which then leads me to my run 2 more times, take average. That helps me figure out if it's just problems with the readings, radon gas, or if it's truly contaminated. Then I know that I need to take actions to clean up that area to make sure that there's nothing anybody can get harmed with, at the same time as try and find out where the contamination came from and be able to prevent it from happening in the future, because the less contamination of an area we can have, the better. Of course, there are situations where that will be difficult. The best thing we can do is just monitor and be ready to prevent the contamination from being spread and cleaned up as soon as possible, and keep people in a safe environment where they aren't worried about their health. Okay, so the stack effect. It's caused when negative pressure differences exist between the interior and exterior of a building. It draws in radon from the soil. So once again, going back to radon's really dense. It's naturally occurring within our soils. Once again, that's the reason when it comes to basement laboratories such as the reactor bay, or for another example, if needed, in the physical science, we have a bunch of labs in the basement. So due to weather changes, temperature differences, because buildings are heated up or cooled at different rates than outside, so we can remain comfortable all year long, right? So these temperature differences, when it comes to weather, etc., causes especially lower basement areas to bring in more of this radon gas, which makes it to where it's easier to be picked up. It's caused by the decay of uranium-238, I believe. I should have wrote that part down. But yeah, it's a naturally occurring gas that we do pick up on our instruments. That's something to also keep in mind when you're frisking something with a meter, the Geiger-Miller tube. It's always good to check for background, because radon will be counted into that background. If you're getting higher numbers in an area, it's one of those. It's always good to keep in mind. Okay. Oh yes. A bunch of you heard me talk about the action level a slide or so back. So ISU's action level for the time being is 70 disintegrations per minute per 100 centimeters squared. So when I do a swipe of an area, it's 100 centimeters. That's what I'm shooting for. I usually do an S motion, but what you figure for is 100 square centimeters is about the size of a dollar bill. So when you do the swipe, you want to cover that kind of area, because that'll tell you what kind of radioactive contamination there could be within that said space. And if it's a high enough concentration, once again, 70 dpm per that space, that tells you it's contaminated and we have to go back in and clean that area. But an action level is a level of removable contamination that, if exceeded, must be addressed to lower the level to within our limits. Within our limits is none, right? We don't want them even close. Yes, if it's below 70, it's safe, but once again, we don't want it approaching that, but it can be helped. The cleaner we can have something, the better. We don't want to be causing contamination if it can be helped. But at 70 dpm, then it's one of those, it's high enough activity that we need to address it. We need to make sure it's cleaned. But our critical level is still radioactive. Still has radioactivity and has to be dealt with as being radioactive. Oh yes, signs and labels for rad and rad areas. Okay, kind of the common sense thing. If something is labeled as radioactive, then the best course of action is to treat it so. So if it has a radioactive sticker on it, figure it's on there for a reason. Something's contaminated, it emits radiation, treat it with care. It's, once again, radiation is not to be taken lightly, it's to be respected. It's not dangerous if you treat it properly. So it's one of those, if there's a radioactive sticker on it, just figure it is. It's the best bet you can do for your own safety. If it's because something was radioactive there and it's in the process being decontaminated and made safe, then it's better to know that's in the process of doing so. Until we know for sure that's safe, then the label should be removed. But if there's a sticker, it just figure radioactive, contaminated, keep your distance unless instructed otherwise. Also, items that are labeled radioactive, keep them separated from non-radioactive things. So if you have it labeled, let's say pair of pliers have been labeled that they are radioactive. The best thing to do is not toss them in the glove box, right? We don't want to contaminate more things. We want to limit the amount of contamination we have. So the best thing we can do is keep them separated until they are cleaned and they come back as perfectly safe. Nothing's wrong with them. We know that there is no contamination that can be spread by them, and they are no longer emitting any kind of radioactivity. So yeah, trust labels, trust signs, just like when we're operating, we flip all the signs to warn people, hey, this is a radioactive area, or this is a high rad area. It's one of those signs and stickers are there for us so we know how to stay safer. That's the reason when we fire up the reactor, we flip the signs. You read differently than when everything's shut down, when there's less to be worried about. Okay, radioactivity. What is it? The emission of energy in the form of waves or particles in any attempt to become stable. So pretty much as an isotope's decaying, it's trying to leave a state where it's excited, trying to, well, let's use the idea of this is going to be a weird example, a baby gave sugar to. They're bouncing off the walls, right? You hand a little kid sugar, they're bouncing off the walls. Well, them coming down to nap time is the radiation. They're giving off the radiation as they run around circles, driving us all nuts. So that, which then brings them down to a stable level, which is nap time. So there are different types of radiation. There's there's alpha, beta, gamma, and ion. So alpha can be stopped with a thin piece of paper. It's one of those, it's easily stopped. It can't make it through many barriers. Beta has more strength. It can go through more. Gamma, it's very dense things, slow it down. Such as like lead. Lead is a very good barrier between it. But it will go through most things. Then ions are ionizing radiation. It's one of those interacts with things like polyethylene. That's a good thing to interact it with. That's the reason our rim balls have a giant piece of poly. It's to pretty much get the neutrons to interact with it, to where we can get a reading so we know how high of a radiation area we have due to ionizing radiation. So different kinds of radiation that we come across every day would be like the sun. Anybody that thinks the sun isn't giving you radiation, I don't know where they think a sunburn comes from. Bananas, if you eat bananas, you're getting, it does have radioactive isotopes within it. Has radioactive potassium isotopes, I believe, within it. And then the old Fiesta dishware, the stuff that was made between 1936 and 1972. The glaze they used was a depleted uranium oxide, and that will emit radiation. Some people use it as a check source because of it. Over at EBR1, for a little Geiger Mueller, for what were they using? It was a pancake frisker. It was pancake frisker. And to check source it to see if it was reading properly, he used one of those Fiesta dishware plates. Of course, modern ones, anything past 72 has a different glaze. But between those times, that's what they were using for that kind of glaze. Of course, there are many different things that have that emit radiation in our everyday life. Soil has certain amounts of radiation built into it, like I was talking about the radon gas. There are many things that give off naturally occurring radiation. Heck, light is a kind of radiation, reading the part of its particles and waves. The forms of waves, well, light is a wave. Okay, so dose versus exposure. Exposure rate is the measurement of the intensity of the radiation field you are exposed to. The measure of radiation dose you receive is the absorbed dose rate. So that's a way to think of with the dosimeters. Like using the pen dosimeters, it tells you how much was absorbed. It tells you what your body took in. So using this kind of idea, the dose slash exposure rate is like speedometer. It's how many are in the area, how fast are they coming through. The dose or exposure that you are receiving is like the odometer. It tells you how fast you are turning. The odometer in a car is telling you how fast the engine is turning over itself, how fast the car is internally taking in, how much energy is being given off. So that's a good way to think about it. The amount of exposure is how fast things are moving around in there. That for exposure rate, how fast things are moving around in there. For personal exposure, it's how much is going on inside. For you personally, how much radiation are you taking in? That's a pretty good way to think about it. Hopefully I didn't make that too confusing. Sorry if I did. So if you want to look into more of the regulations for ISU, this is where you can go. It'll take you to the EHS radiation safety page. At the top of the page, there will be a link that says Radiation Safety Manual. And if you click on that, it will open a PDF of the Idaho State University's Radiation Safety Manual. And that will give you a place where you can reference to find out different information, such as like about our broad scope license that ISU has, about different ways of dealing with radiation, who responsible users are, what their responsibilities are, what their things are allowed, what are not within our broad scope license. So yeah, if you have questions I haven't been able to answer, that's a good place to go for finding answers. Of course, the SAR is another good one, and tech specs are also a really good one for extra little information about different little intricicities to know what to do in certain situations and how to treat different things. I hope this was helpful.